Let's finally look at the underdamped case. So this is where gamma is small, and we found that gamma squared less than 4 mk. We found that these are our complex roots. And we know how to interpret the real and imaginary parts, a little bit at least. The imaginary part ends up being a frequency, like an angular frequency, and the real part is the exponential, is the rate on the exponential factor that sits in front of everything. So you're seeing that this is negative, right? So you have an exponential decay factor sitting out in front, and this is the frequency. So that's pretty neat. Maybe looking at it, well, yeah, let's just work out the general solution. So here, the general solution will be x of t equals, and let me do it in this order instead of immediately giving you the general solution. So I'll give you the general solution at the end. X of t equals c1 times something plus c2 times something. But to get those somethings, what do? We take one of the complex solutions, and then we take the real and imaginary parts, and those will give us two linearly independent real solutions that we can stick here. So what's one of the complex solutions? It'll be e to this thing times t. So complex solution that we got, e to the, let me just copy it over. Okay, there, it's copied over, and times t here. So e to that thing times t. And that we could break up like this, e to the negative gamma over 2m t times e to the I, this thing. So maybe I can find a better way to write this. How about I stick the 1 over 2m inside, kind of like I was doing way back here in the first video. So that'll become 1 over 4m squared inside. So that's k over m. Nope, k over m. Minus gamma squared over 4m. Or how about I write it like this, gamma over 2m all squared. And then all times t. Okay, and that's e to the minus gamma over 2m t times, so when I have e to the I something, that's cosine the something plus I times sine the something. So that's the principle that we use to get the real and imaginary parts. So I've just copied this over, and then it's times, or let me distribute it. So the first part will be cosine that thing times t plus I times, and then I'm distributing this thing, so that's still hanging around there. So I times sine of the same thing. Let me be lazy here and copy it over. And it looks like the k lost its body. Okay. So the purpose of doing that is that we now can see the real and imaginary parts of the complex solution. So here, this is the real part of the complex solution. Let me just stick that here. Let me give it room. And stick that here in front of that C1. And here's the imaginary part, which is, notice, is real, if I can select it properly. This is the imaginary part. And I can stick that here, except now it's partly off screen. So let's do that. So there's my general solution. Very nice. there's my general solution, and this is assuming we're in the underdamped case. So this is all assuming assumes gamma is small enough, where by small enough I mean its square is less than 4mk. That's what is needed to guarantee that this square root makes sense. So if you didn't have this condition holding, then this square root would be the square root of a negative, right? Or I guess it could be 0, but yeah. Okay, now let me try to write some better plotting code than I did last time. So let's define, let's basically write down this thing here. So I'm going to make it depend on not just t, but also c1, c2, just so I can have an easy way to refer to this expression as a whole in its dependence on not only t, but also c1, c2, and gamma. And I'm going to keep m at 1 and k at 1. We mentioned in the last video why that doesn't hide anything from us, because units could always be chosen to force these to be true. Okay, and I'm also going to include the dependence of x on gamma. That's not how I was writing it last time. Okay, then I just need to copy this stuff over. Okay, there's the first term, and I can copy and paste to get the second term. So c2 here instead of c1, and just sine instead of cosine. All right, and let's start trying some plotting. So here's my initial plotting command, and it's not going to do anything because c1, c2, gamma are unknown. So you can see, you know, I've only fixed m and k, so there's nothing to plot yet. But let's make at least c1 and c2 be something you can change by dragging some bars around. And then let's make gamma, let's just fix a choice of gamma. And we cannot just pick anything for gamma, we have to pick something that makes what's under the square root be positive. In other words, we have to pick something that places us firmly in the underdamped case. So gamma is not allowed to be too big. Okay, so I'm going to pick for gamma for now, just to make a plot. So I've got to pick something smaller than 4 times 1 times 1. So anything something whose square is smaller than 4 times 1 times 1. So I can pick any gamma less than 2. So how about gamma equals 1? All right, this is what I have. Okay, I need to fix the plot range so that the axis doesn't move around on me as I move things. There. So now looks like that, and I feel like I'm not seeing enough of it to really get a feel for it. So how about we run time out to 50. Let's make it 30. Okay, so you see changing c1 and c2 changes some of that initial behavior, but you still get ultimately decay to 0. But what we're changing is this kind of initial portion. So this initial portion is always called transient behavior. So this is like the transient part. I mean, actually, so yeah, we'll introduce that term transient later on in the course. But the entire thing decays, right? The entire thing has a big fat e to the minus gamma over 2mt sitting in front of it. So the entire thing decays to 0. And what you're seeing here, actually, we set m and k and gamma to be 1, right? So what's our differential equation? It's like x prime prime plus x prime plus x equals 0. I'm pretty sure that's the example we looked at in the last lecture. So we're literally just looking at that example. So this is our, decaying oscillations example, where you have a sort of exponentially decaying amplitude. But the oscillations keep going on. So let's see if I make this vertical range smaller, maybe like 0.2. You can see for longer, so same horizontal range, you can see that the oscillations keep going on. Let me make this even smaller, 0.05. You see? So it's kind of like the spring just goes, you stretch it out, let go, or whatever, and it just goes, whoa, and it keeps oscillating about the origin, but with the amplitude decaying. Okay, so that's the underdamped case. So we can figure out the period here. Again, it's not exactly period since it's decaying oscillations, but we can figure out the exact period and how that period depends on gamma. So that period is, since we have the angular frequency, where'd that go? Over here. So here's our general solution, right? Even before having the general solution, just looking at the imaginary part of our root of the characteristic polynomial, just looking at this imaginary part, that's the angular frequency, right? But here it is showing up again inside the sine and the cosine in the general solution. So you can use this to figure out the period. So like, what was it? The angular frequency tells you how many radians there are in a unit of time. I'm not going to say seconds, since the units of time are sort of whatever forces k to be 1, right? But the angular frequency has units of, so we have this many radians in any unit of time, whatever the units of time are. And if you want to know the period using those same units of time, then I guess you want to take the reciprocal of this number, so that you have how many units of time it takes for 1 radian of phase to pass, then multiplied by, well, now you need to know how many radians there are per unit, per cycle. There are 2 pi radians in a cycle. So 2 pi divided by this number, that's the period. So let's see if we can make a prediction. What do we think is going to happen as we change gamma, as we change the damping? So let's say I keep m and k fixed at 1. What do you think would happen if I change gamma? Do you think the oscillations are going to squeeze and become tighter, higher frequency, lower period? Or do you think that they'll become bigger? So make a prediction based on what you're seeing here. Okay, so pause the video and think about it. And now I'm going to assume that you have made a guess, and let's see what happens. Okay, I've modified the code a little bit so that now I have a bar where I can change gamma. And this, right now it's set to the previous value of gamma, which was gamma equals 1. And now as I change gamma, let's see. So I'm going to increase gamma, and hopefully you have made a prediction as to what will happen to the period or to the frequency. So let's see what happens. I increase gamma. It looks like the frequency gets slower, or the period gets larger. If I decrease gamma, it's actually quite subtle, right? The changes in amplitude are much more pronounced. Yeah, it's really a subtle effect. So I think the changes in amplitude are looking unnaturally pronounced, partly because I'm arbitrarily choosing to fix C1 and C2, rather than, while I change gamma, rather than fixing, say, initial position and initial velocity while I change gamma. Okay, so let me see what I think. What do I think will happen when I increase gamma? Just looking at this, this is the period, right? If I increase gamma, then this term will increase, gamma over 2m squared. This will increase, but it's being subtracted here. So what's inside the square root here will decrease, and so the denominator here will decrease. that will cause the fraction to increase because the denominator's decreasing. So the fraction will increase. So I expect the period, which is this, well, which is this, including the 2 pi part, which is this. I expect the period to increase as I increase gamma. And boy, it is really hard to see in the plot. But you can kind of, like, look, measure from here to there. As I increase gamma, it does grow, right? Okay, let's now go ahead and replace C1 and C2 by actual initial condition values, like x naught and v naught, initial position and velocity. So I've got x of 0, C1, C2, gamma. Let's do everything in terms of unknown gamma. That's actually just C1, so that's nice. And then let's look at x prime, well, not x prime, but the derivative of this thing with respect to t. It's this complicated stuff, right? 4 terms, because you have to do product rule on two of the terms. But then we plug in t equals 0. We should only have 2 terms there. And now there are 2 equations I'm concerned with. This one being set to the initial position, and this one being set to the initial velocity. So, oops. So these are my 2 equations. So let's now solve these 2 equations. And yeah, it's really easy to solve the equations, but it's easier to copy and paste things. For C1 and C2. And this tells me what C1 and C2 are in terms of initial position and velocity. And this time, unlike last time, I kept the gamma in there. So let me go back here, and let me copy this stuff over. And let's do this again. But this time, instead of C1 and C2 being what you manipulate and watch changing, this time it'll be x naught and v naught. Oops, there. Yeah, so here this is x naught, this is v naught. And let's again allow you to change gamma between 0 and 2. So why am I choosing to allow gamma to go between 0 and 2? That's because those are all of the underdamped values, right? Underdamping is when gamma squared is less than 4 mk. I've set m and k to 1, so this is just 4. When is gamma squared less than 4? Well, when gamma is less than 2. So, and gamma is always positive, otherwise it's not it's no longer a physical situation, it's not damping. So gamma between 0 and 2, that's the full range of possible underdamped situations you can have. Okay, and let's look at it. So it's starting out looking like that because, okay, so let me set my plot range to 3, since I seem to like having x naught vary from 3 to negative 3. So, okay, let's set the initial velocity to 0, since that's an easy situation to imagine. That's where you pull the spring away from equilibrium, and then you let go from rest. You let go from rest. And, well, if I set x not to 0, of course, then that's just having it at equilibrium and letting go from rest. It's not going to go anywhere, right? It just stays at equilibrium. But if you displace it a certain amount and then let go, then it oscillates. And there's no decay. Why? Because gamma started at 0 here. So there's no damping, so it just oscillates. That's it. And it oscillates with a certain frequency. What is its natural frequency of oscillation? It's, where'd it go? This was the period. This is the, this is the angular frequency of oscillation. If gamma is 0, it's just square root k over m. That's what we found very early on when we analyzed the system. Square root of k over m is the angular frequency. So that's what we're seeing. And if you displace it more, then you get, like if I set x naught to be about 2, then it starts displaced at 2 and then oscillates with an amplitude of 2 to whatever units of distance we're using. Which, by the way back when we were discussing unit choices, we never put any restrictions on the units of distance. So units of mass need to be chosen to make m be 1. Units of time need to be chosen to make k be 1. But units of distance can be anything. So it could be meters, actually. Yeah, so 2 meters it could be. Okay, so let's tune up the damping. You can see what happens as you tune up the damping. The most pronounced effect is on the later amplitude, right? The amplitude is decaying. And if you run this for long enough, if there's any damping, even if there's just a tiny, tiny bit of damping, if you run it for enough time, so right now it's just going from time 0 to time 30, but if you run it for enough time, sorry, it reset all those values. So let me go back to some displacement, like 2. Release from rest, and a tiny gamma. So even a tiny gamma, you see the shape here? It's this exponentially decaying amplitude. So it eventually decays. And if you make gamma larger, then it decays very quickly. Okay, let me go back to just 30 here. And let's try not releasing from rest, just because that's also fun. So releasing from rest looks like this. If I stretch it out to position of 2, and then release from rest, pretty much rest, it looks like this. If I stretch it out and then throw it so that it's even more being stretched out, so that it has initial velocity like that, then I'm looking at that kind of situation. You're giving it more amplitude, right? And you can see the slope at 0 is now higher, bigger. So that's fun. Yeah, and of course, when you make V naught be negative, that's like stretching it and then throwing it back towards the equilibrium. If you are kind of giving it energy by throwing it in either direction. So if V naught is 0, then you have this sort of low amplitude, but high V naught or even high negative V naught, both are you giving this more energy to the system. And then gamma does that. Okay, I think we're done playing with this. And before we end, just by the way, the mechanical, the electrical circuit with a resistor, capacitor, and inductor in a loop like this had the same exact differential equation, pretty much, as this one that we started our lecture today with, as this one. It's just that m and gamma and k have been replaced by other things. So, and I of t is now being used instead of x of t, where I of t is the current through the circuit. Or if you didn't want to take an extra derivative, you would have ended up with q of t, the charge on the capacitor plates. But it's the same deal. What's going on here is the same. You're going to end up with 3 cases depending on how the constants L, R, and C are related. Either overdamped, underdamped, or critically damped is the unrealistic, perfectly in between case. And who's playing the role of the damping is the resistance. So that means there's some magical resistance value where if the resistance is beyond that value, then oscillation in the circuit is snuffed out. And if the resistance is below that value, then you're underdamped and you do get oscillation. So that's kind of interesting. One of your homework problems will be to figure out what is that special resistance.